In this Mind Bite we look at the spectrum of a angle modulated signal. That's either a frequency modulated or phase modulated signal. These signals come in two different flavors, either narrowband or wideband, and we'll talk about the difference between these two. In practice, narrowband is only ever an intermediate stage to producing a wideband signal. So here's our revision of what an angle modulated signal looks like. Remember, the angle part is inside these brackets because cosine can only work on an angle. We change our phase phi to either implement phase modulation, where the phase is just proportional to the message signal, or frequency modulation, where we set the phase proportional to the integral of the message signal, which in effect sets the frequency to be proportional to the message signal. Now from now on I'll only be talking about frequency modulation, but in fact I mean any angle modulation at all. So we use the expression that our modulated signal has an amplitude AC and it's the cosine of our carrier frequency component plus phi, the phase, which has our message buried in it. And we're going to use the rule for cos A plus B is equal to cos A cos B minus sin A sin B. So the cos term here and the sine term here are just the carrier. This is the cos of the part carrying information, and this is the sine of the part carrying information. Now we're going to make the assumption that our phase phi of t is small compared to pi upon 2 or 90 degrees. Now we can make that happen just by changing our modulation factor. Using our Taylor-Maclaurin expansions, if phi is sufficiently small, then cos of phi is very close to 1, and sine of phi is approximately equal to phi. So this is throwing away the next term, which is phi cubed, and this is throwing away the next term, which is phi squared. So to first order, this is correct. So substituting this cos for 1 and this sine for phi yields this expression down here. Now you'll note that the first term, this term here, only has carrier information in it. There's no message signal in there. So that is just broadcasting the carrier wave. The second term is an AM, an amplitude modulated signal, because we have a carrier, it's a sine, but that doesn't matter, whose amplitude is modulated by phi, which has our message buried in it. So narrowband FM is very similar to amplitude modulation. There's a carrier term and a term where the amplitude is modulated by the phase. So what's the power spectrum of this narrowband FM signal? It's got these two terms, the first term minus the second term. And you'll know that because Fourier transforms are linear, that means we can work out the Fourier transform of the first term and subtract the Fourier transform of the second term. The second term is a product of two functions, phi, which has our message signal in it, and sine. And where you have a product, you're going to have to use a convolution. So here it is graphically. The first term is just a cosine of a carrier frequency, so its spectrum is our classic cactus. Phi of t is the part which has our message buried in it, so I'm going to assume it's band limited and has a bandwidth from DC up to omega max. Sine has a spectrum much like cos, except the delta functions are imaginary, that's why they're dotted, because they're in the j direction, and they have opposite signs. The positive frequency is positive and the negative frequency is negative. So we need to find the convolution of this, our message spectrum, with our sine spectrum, and subtract that from our cactus spectrum for the carrier. Now here we have the result of convolution of our message signal with our sine spectrum. Where our sine spectrum had a positive delta function, we now have a copy of our message spectrum. Where it has a negative delta function, we've got a negative copy of our message spectrum. We now want to find the difference between these two. Clearly the difference is going to have both real and imaginary parts, and it becomes difficult to represent on a graph. So at this point, rather than doing the amplitude spectrum, we're going to look at the power spectrum, which is only positive. And this is the power spectrum. It has the two delta functions at the carrier frequency, which come from the carrier term, and it has two copies of our message signal spectrum centered on the positive and negative carrier frequency. So the power spectrum is very similar to double sideband amplitude modulation, and just like amplitude modulation double sideband, the bandwidth is twice the bandwidth of our message signal, and so it has the same disadvantages and advantages of an AM modulated signal. So all this hasn't gained us very much. The narrowband FM has the same power spectrum as amplitude modulated double sideband, and so it only gives us very small improvement on SNR performance. The signal to noise improvement is due to having the constant large amplitude. It is not broadcast very often, but it's often used in intermediate stage on the way to producing wideband frequency modulation. Wideband FM has a much wider bandwidth, up to 10 times that of the message signal, but gives you very good quality signal reproduction. We're going to use the Taylor-Maclaurin expansions again. Remember previously we cut off our Taylor-Maclaurin expansions at just the first term, so 1 for cos and phi for sine. Now we're no longer going to be able to assume that our phase phi is small, which means these later terms are going to be larger, which means we're going to have to use more of them. This means it's going to be pretty messy. Yuck! So this is the same expression we had before. Previously we'd simplified our cos of phi of t as 1 and our sine of phi of t as phi, but now we're not going to be able to do that. We're going to have to substitute these expressions in for cos and sine, and so it's going to get quite big. Here we go. We have the first term, the carrier part, and this is our Taylor expansion for cos. This is our carrier part again, and this is our Taylor expansion for sine. We're going to go through and write the power series, collecting terms of ever-increasing powers of phi. We have a 1 here, that's equivalent phi to the 0, and that's the lowest power present, and it has a multiplying factor of cos at our carrier frequency. So that's this term here. The next highest power of phi is phi to the 1, comes from this term, and it has a multiplier of sine. So that's this term here. The next highest power, phi squared, has a cos again, and the 1 upon 2 factorial. So here we are, phi squared cos 1 upon 2 factorial. And you go on alternating between these two expressions, picking out the terms in phi cubed, phi to the power 4, etc. Now we have to work out what the spectrum looks like for this expression. I'm going to state, just by blatant assertion for the moment, that the bandwidth of our cos, well, our cos only has one frequency present, which is the carrier frequency. So it's got no bandwidth at all, it's just a delta function at the carrier frequency. Sine, well, we know that if we multiply phi by sine, then we get a bandwidth that goes from our carrier frequency minus omega max to our carrier frequency plus omega max. Right, so this has bandwidth 2 omega max. Now this one, phi squared, I'm going to state, has a bandwidth of twice omega max, and when you multiply it by cos, it upshifts it to be around the carrier frequency. So it's the carrier frequency minus 2 omega max to the carrier frequency plus 2 omega max. So it's got a bandwidth of 4 omega max. You can see that each time you go to a higher power of phi, then the bandwidth increases by 2 omega max, because the negative gets smaller and the positive gets higher. So the question is, why does phi to the n have a bandwidth of 2n omega max? To understand that, we have to look at what the convolution. So let's say this triangle is the spectrum of our message signal, phi. How wide is phi times phi? So how wide is the spectrum for phi squared? Now, in the time domain, if we multiply, then in the frequency domain we need to convolve the spectra for phi with itself. And so here we have the sort of flip, slide, multiply, integrate, which is the way we implement a convolution. So here we have the spectra for phi. We've got the original one and the flipped and shifted one, and here they're only just overlapping. It gives us this first very small part of the convolution, and that occurs when they span twice the bandwidth of just one of these spectra alone. As you slide this one along, eventually they lie completely on top of each other, and you get this point up here, and when it's slid along to omega max, then it's just touching on the other side. So you end up with a spectrum that's twice as wide as the spectrum of phi. You can imagine that if we did this again, if we calculated phi to the power of 4, then its spectrum would be the convolution of this one with itself, and it would also be twice as wide again. From this we can deduce that the width of the spectrum is proportional to the power n that we raise our phi to, a phi to the n. So phi squared has a spectrum that's twice as wide as phi. Phi to the 4 has a spectrum 4 times as wide as phi. So the spectrum of our wideband frequency modulated signal is a weighted infinite sum of signals with bandwidth 2n omega max, where n is the power of phi. Fortunately, as the terms get wider, this n factorial on the bottom line gets much bigger, and so they're multiplied by an ever smaller number. By the time we get to the 10th term, when the spectrum is twice as wide as the original baseband spectrum, we end up with a term that is 3.6 million times smaller than the first term. It's 130 dB smaller. Therefore, we can just throw it away, and we can throw away all later terms than that. This will be what the spectrum looks like after we've done that infinite sum. You can see that the bandwidth is much wider than the bandwidth of phi, represented by omega phi. But as you get up to 4 or 5 times the bandwidth, the power at these frequencies gets very small, and we can just chop off our sum there and throw the rest away, not bother to calculate them. So wideband FM has bandwidth that can be as much as 10 times more than an AM double sideband signal, but it's still used. You know that your classic FM stations use wideband frequency modulation, and they do that because it gives much better signal fidelity than AM, because you're always using that higher amplitude. Also, you have a lot of redundancy because you're using so much more spectral bandwidth. So historically, amplitude modulation was used for a long time before frequency modulation came along. And actually, frequency modulation was a hard sell to begin with. It was resisted for a long time because of the amount of spectrum it would use, and the thought that will everyone go out and buy a new radio with FM capabilities? Well, we all know that in the end people do, and that's why we have FM stations today.